Good morning. I'm able to finally get started to make the recording. For those that won't be here today, which may be more than one person is reported not coming though because they have a cold, which, you know, the weather's changing back and forth. This is the time of the year when it happens to a lot of people, right? So I'll just update you on the grading progress. I've made good progress. I was going to push a couple of them back while I was eating breakfast. They're totally done. I'm in the process of grading 2 others, and then I have a 3rd one that I've glanced at but haven't done any marking on yet. My goal is to have those all done today, and I'll push them back. And I'll push back, put a histogram up probably on the web page. So what I'll probably do is, what I'm thinking of doing, I can do it a number of ways, but I can go inside here and I can just tack another thing on here that says histogram or something like that. So you can see in the histogram will have the mean on it as well. Everybody's, of the 2 that I've graded all the way through, and I guess the other 2 that I've graded the first problem on and parts of others, I'm saying variations, but the scores right now, there's 116 points. The scores have been like 102 and 100 or something like that. And what I've done is I've just taken points off for things that aren't quite right. The problem that had the black box systems is probably the one that, you know, has caused the most trouble. But there's other areas. There's other careless errors, I guess I would say, too. It's nothing really to worry about, because if I'm consistent and everybody's making similar mistakes, which is what I'm seeing, it just lowers the average down, but it doesn't really have that much impact. I'm just wanting to be as helpful as possible, and I want to be consistent as possible. One of the things I have observed in grading, though, is that at least one person is clearly using solutions they found on the internet, which I consider that to be the book solutions. I consider that to be cheating. I mean, you don't just copy that into your solution. So, you know, I'm not getting really mean about it, but I am writing about it. Just don't do that. Just do your own work and let me see that you're understanding or not understanding it, because it doesn't prove anything to just copy something and say, here it is. Well, I don't like using the solutions, manual solutions, unless I'm desperate to help explain something, and I did do that for one of those black box problems. So the black box problems were early, so I gave you that just as a challenge, not to say you'd be perfect at it, but just to kind of be challenged into thinking. And we can talk about that if that's something that you'd like to do too. Right now, I just want to get back over, unless there's other questions, to the Fourier transform. We'll move along on that, and I'm optimistic that if I can push hard, I'll be able to start the Z transform before the day is over with. So meanwhile, back to where we were, and of course I have my tablet here with the solutions, and we can go over the homework problems that are due and kind of elaborate on some of the hints that are out there. So I've got to scroll back up to where I was. Last time we left off, we were in this area, and I'm going to expand this out. And now that I'm looking at this, if this tool that I have both on my iOS iPad and I have on this machine, it's called Drawbox, they've been pestering me because I did a demo of some of their advanced features. They have a special student and teacher discount going on right now. You can get it less expensively, and it provides pretty good capabilities. I'm really picky though, so I'm using it to grade on my tablet, and I've been using it to teach on for a very long time. But now I have extra tools in here because I've got this demo going on, and they'll all go away if I don't officially pay for the upgrade. But from what I've seen, another thing I've seen in all the papers I've been looking at, all of you are very good at using your tablets or whatever devices for doing it. Some people are scanning. Most everybody's writing right on their tablet device. And everybody's unique, right? You're all individual. I don't know what tools you're using, but I'm seeing pretty high quality stuff that I can easily see, and I can zoom in and out easily, and I can write on it on the iPad version of the same software, and it works well. And I guess if you have a routine, I'm not asking you to break it. My idea of bringing in the computer solutions was to go to Jupyter and export out to Markdown and then convert that to PDF. I still like that a lot, but if you'd like to do screenshots and paste in, that works well too. I did that for longest time, but again, individualized. Some of you are very particular already, and that's fine, because that's what engineers tend to do, is they get very specific on how they want to produce anything, and homework is no exception. So some people want to drive it to the limit, and I don't want to halt you from that. I want to encourage you, if you want to push that hard, you can make it happen.
How would you save that from Jupyter Notebook to a PDF, other than print the PDF?
What I do, I guess I was gonna demo that one day, so I can jump out of this for a second. What I do is I will go into my notebook here, and let's just take this as a simpler one. This one I demoed last week with this guy right here. So what I would do, you get these options, and you have Save and Export Notebook, and you see all these options in here, but unfortunately most of these will not work without extra open source tools being installed on your machine, and they tend to be very finicky. You know, you can get them to work like the LaTeX version, or PDF directly via LaTeX, which you have to have installed on your machine, is very beautiful and nice, but it's very much a pain to get going. So the one that always works for me, though, is to export as Markdown. So I'd export it as Markdown, and it's doing that right now, and it's going to create a zip, and probably because I'm running the video screencasting here, it's taking longer. Everything seems to take longer on this machine, but it should produce a zip eventually. There it is. Okay. So now there's a zip, and I've actually already got one of those in place, but so I would go over to my downloads folder, and I just have to get over there. So I'd go to downloads, and I could go look inside there, or I could just boldly go and down and unpack it right now. So I'll extract all. Go folder, and then there's the Markdown file. So what I would do at that point is I can go preview that Markdown file, and I've got this little thing I downloaded from the Microsoft Store called Quick View. If you have a Macintosh, you have Quick View kind of all the time, but you can get the same thing here on a Windows machine, and actually this is nicer. This is actually a nicer program than what Apple has. This one can preview all kinds of different files, and it's already previewing this Markdown file converted back to HTML, so you're not really seeing the true core of it. But so you'd be able to go with this, but then what I would do if I was doing this, I would go bring up my VS Code, And in that document on the web that says installed Python with Julia, I have at the very end of that document the instructions on what extensions you want to have installed here in VS Code. So I've already got a markdown file open up, and I'm going to navigate over to another location to get there. But if you install VS Code, while we're waiting for this, I'll just jump back over here. What I'm looking at is, if you go in here, this particular document on the website has a back section of it that talks about VS Code. So if I go and open that up, you see I've already got it pointed to that. But if I go to File, Set up and using VS Code. So if you go into that section, it talks about installing VS Code, and it talks about installing a couple of extensions for VS Code, one of which is called Markdown PDF, and then the other one is VS Code PDF, so you can look at PDFs easily in VS Code. So that's kind of where that what that gets to. So now I'll go back over here to VS Code, and so I've already got those extensions installed in here. I have a lot of other extensions installed too, but so I could do Jupyter editing and things like that. But here's Markdown PDF, which I installed, and the other one is in here somewhere. I thought I installed it. If I didn't, I can easily get it installed. This machine was rebuilt just before classes started, so it's possible I didn't install it. But if you have to install an extension, you just type in the first few letters of whatever the extension is, and there it is. That's the one I happen to be using, and if I click on it, it will tell you, it's pretty popular, just like everything in our life. There's stars that how people like it, and they talk about it. So I would just say install that. And it should be on here momentarily. Normally it doesn't take very long at all, but something about being here, maybe just the way things work, it's not that fast. I'll just let it go off and do that. So what I'm going to do now is go and navigate over to my, open up a new window, and in that new VS Code window, you can have as many open as you want to. I'm going to point it to the folder called Downloads. So I'm going to say open a folder, and I'm going to let that folder be Downloads. Okay, it's over here. Okay, so I'm going to say go to Downloads, select that folder. And now that I'm in this VS Code window, I can navigate over to where I unpacked that. And I unpacked it right in here. So there's where I unpacked it. And if I want to now, it still says it's installing. I don't get that. But at any rate, I can go open up my Markdown file, and then I can just see the raw Markdown file, and in order to have math show up in here, I tell you to go over to my setup over here, and I say copy these JavaScript files to put at the header, and so I just put that in at the top. But this will just make sure when I render this back to a PDF, I will get the right stuff included in it for And I might want to get rid of the line breaks that are in here, because I'm not sure whether that'll cause an issue for me. Maybe not. Let me just get rid of that for a second. Okay, it appears as if it doesn't want to alter that, or maybe I've got something not right here. I think it's okay. Yeah, I think it's okay now. Which of the scripts?
Right before.
Yeah, right there, right? Yeah. Okay. So now I can go ahead and look at this file and decide if I want to make any changes to it, edit it in any which way I want to. And I also have over here, this is probably the most important thing, if you have what the export to Markdown is going to do, is just going to create a long scroll just like a web page. But you can insert this. This is actually HTML code. You can insert this where you might want to force a page break. So you can put page breaks around a problem to make that solution show up just on 1 or 2 pages. And that way, when you export it out as a PDF, you can manipulate it to put that in with your solution. You can drag and drop it in if you're using the Adobe tool. I gave a link to that on the website too. Did anybody ever notice that? I don't know what you did to produce yours, because you had Jupyter Lab stuff in your solutions. Okay, like I said, screenshots work. What they do is if you do a lot of them, your file gets really fatter, is what happens. It makes it harder to work with. But I did put a link over here a while ago. I may have actually deleted it, though. It's possible. Yeah, I guess I deleted it. I can put it back out there again. I just searched on Google and said, how do I insert and delete pages from a PDF? And Adobe has an online tool that you can use for free to do that, to manipulate PDFs around. So I won't go look at that. I'll look to put it back out there again. Meantime, back over to here. So I've done that, but let's just say I'd like to break something out of here. Another thing that won't show up on here is the graphics that were created for the graphical controls created like we saw last week when we ran it live. I don't care about that for homework. If you want to take screenshots and merge that back in, you can certainly do that, because you can, right here in this Markdown language, you can add in another command if you want to put a screenshot in, and that's right down here. I can use that. If I had a screenshot of something that didn't render all the way through, I can put my own screenshot in with another HTML command, and then I can control the size of it with a percentage zoom there. So that's what I mean by driving it to the limit. Some people will, get interested and excited about that. But right now, I'm just going to go back over to here. First, I'm going to check to see. Okay. This VS Code PDF is installed. I don't need to look at that one anymore because I've got the new one I opened up. But let's just wrap something here with a page break. Just for the fun of it, I'll put a couple of those in here, and that way you'll see when this renders out that finally finished installing that extension. So VS Code was just saying, please reload it so that I get access to that extension. So now I'll just shift this back over so you can see my file listing. And now there's, because of that plugin that's been installed already, if I want to render this out, one of the things I can do is I can right-click over that tab, and built into VS Code is is a preview for Markdown. So this is a pretty close rendition of what you're going to be getting out of this. But it's not exact, especially if you were to enter in some math equations. But you can do that, but that you still can't print. But what you can do now, though, is you can go Control-Shift-P will bring down all the different commands in VS Code, and this is the one that I've already recently used, export a Markdown file to PDF. So if I click on that, you're going to see that it's going to launch this thing, converting it to PDF, and it will put it into this folder over here. We'll see it show up right in here when it's done. Again, this is not a very big file. It's just taking a long time. There we go. So it's now over here, and now because I installed the previewer right in here, I should be able to open it up, which is what I'm trying to do right now. We got something remnant on here, but here's what it's created. Here's the PDF it's created. And let's just go down here and see if we can remember where I forced a page break. I think it was probably right after this. Yep, it was right after this, and then I forced a second page break. So I managed to isolate these two cells of code because over here is where I put the page break stuff. I didn't do it in a maybe logical place. I just did it to show you how it would do. So it's before this Python cell, code block cell, that one right there, and then I stuck another one before it says save captured samples. So, oops, I'm doing the wrong thing. Getting myself confused here. Go back to here. So is that enough proof to see that I did isolate it? And then if you wanted to tear it out of this PDF using some tool like what Adobe offers or Dropboard offers, if you buy a paid version of it. The Adobe works fine, though. People have used that before. So you can kind of organize your problems. You do all your work in your Jupyter Notebook, and then you put headers in there and things in the notebook to say this is for problem such and such, this is for problem such and such, and then after you export to Markdown, you come in and separate those into definitive page breaks so that you can then tear them out and reinsert them somewhere. Screenshots works fine also, but this is sharper for sure. One person did this in his homework. He did everything in Jupyter and just did this export, and it came out looking fine. It's kind of nice. I use it in different ways myself. Picture gone?
Yeah, I can see there's like an icon of picture, but there's not.
Oh.
Is that the widget?
Now what that is, it didn't export out. We can see how I could get that in here. It didn't leave the export location properly, so I'd have to go manually put it back in here. I could go in here and I could see, okay, I can do a search. I'll just do a Control F, and I'll go PNG. There are some graphics in here. There they are. I didn't want to, that search isn't what I wanted. I think I wanted IMG, but maybe not. Yeah. So we're missing, get rid of that. This search capability in VS Code and change and all that other stuff is extremely powerful too. But at any rate, so this is where that is. So what I would have to do, I have to go back to the source file. So what I'd probably want to do to get that is I'd want to go back over to here, and then I'd want to go navigate into the folder where I had that notebook, and I think it was in 4680. notebooks. There it is. I'm using quick view again, so see, I can just look at a PNG and see that's one. So I could go this, and then I should be able to go over to here, and I could go, should be able to paste, but it's not letting me paste right now. So I can get inside that folder though, which I can get to from over here too. Okay, see now it's in that folder, and if I go back over here to VS Code, it says, there it is, it's in there, and lets me preview it right inside of here too. And now what I could do, go back over to here, and now it should be able to find that. I could do the quick preview and just see that it does find it. There it is. This is quicker, but if now I could go back and re-render it, Control-Shift-P, and I'll say export this to PDF again. And now the PDF that's in the folder over here is going to get written over, and when it's done, it should automatically reload it into this tab. I should be able to see it, that it's there. Okay. So slow compared to my other laptop, but yeah, it's struggling to reload it at the moment.
What do you think is the cause of the speed of that?
I attribute some of it to the fact that I'm screencasting right now, and this is an older laptop. When I left the university in fall 2022, I bought a new XPS 15 with 32 gigs of RAM and fast video on it. That runs really well. It's not a fold-over tablet, but it does have a touchscreen, so I've thought about switching to that. But I don't have the licenses for my screencasting software on that machine, so yeah. I can just go back over here and click this again. There it is. Okay. So now it rendered properly. Proof. Driving it to the limit, which takes an infinite amount of time. But I gave you a little tour of VS Code. And in VS Code, since I'm here, I can do Control backtick on the keyboard, and I can launch a terminal from right here. And if it gets started, which it's slow to getting started, I should be able to go launch Python. Yeah. See, there I am in my familiar prompt. I could do conda environment list. I'm not going to launch them. I'm just going to prove that it's there. And I could go ahead and switch, and I could run Python right here, or I could open a Jupyter Notebook right here. But there's nuances that are associated with that. So I'm just letting you know that it's here and you can do it. And if you're doing debugging of Jupyter Notebooks, that works pretty well here. Remember, I showed you how to debug right in the Jupyter Lab notebook. Has anybody tried that? In my work right now, what I'm doing for ARCA, I'm using it a lot. And I'm really liking it, just staying right in the Jupyter Lab notebook, because the people that created it have spent a lot of time. Microsoft jumped on board and tried to create their thing. Theirs is probably a little bit better, but there's, you know, I'm sad to say, every tool has got pros and cons. I find every tool has something that another tool doesn't, but it lacks something that another tool doesn't have. So it's like going grocery shopping. I'm going to buy this product because it has this that this other product doesn't have, or, you know, vice versa. So you just have to be, I don't know. Years ago, I coined the phrase being a software connoisseur, meaning to say you have lots of choices, and you pick the one that suits your needs at that time. the VS Code, if we end up doing something in the project where we need it, I will spend more time showing you how to get it set up. I use it a lot as well. But right now in my work, because I'm so focused on just writing Python, doing Python modeling, that I'm trying to just stay in Jupyter, and I'm also on a work computer where I'm extremely in a box where I can't put much software on the computer because it's controlled by the IT group. So that's approved, VS Code is approved, and everything Microsoft is approved. So I was making PowerPoint slides yesterday, which pretty much everybody has to do that too, right? I mean, because you have to be able to communicate, and I've got to do some more of that after yesterday afternoon's briefing experience, which went well. But I also did a lot of demoing in Jupyter, and the math equations I put in my Jupyter notebook, which you've seen me do here, those were very helpful to the systems people that I was talking to. The math is just right there, and then the code block's right there, and you can look at it, and they were, I mean, these are people I've worked with before. It just engages the process. I encourage you to do it. I don't know how many other people do that in their work environments, but I find it to be pretty handy to do that. And I could do Julia in the same notebook if I wanted to with the same math, and that is exactly how I produce the solutions. The solutions that I did in the Julia version for set number 1, all of the Python or all of the Julia code inserts came from doing it in a Jupyter notebook, except it was running Python. I exported it as Markdown. I parsed out the problems just like I showed you, and then put it together that way. So that definitely works. Okay, so back over to the Fourier transform. We talked about this at the end of the class last week. This is our forward and reverse Fourier transform expressions. We can do the synthesis for x of n, which is the first equation, from the frequency response or spectrum, and then we can generate the spectrum from the signal or sequence x of n. And of course, we learned first that we get the frequency response by Fourier transforming the impulse response. So that was kind of a no-brainer there for that. And when you're doing x of n, in other words, inverse Fourier transforming, this equation up here shows interval from minus to plus pi. You can pick any 2 pi interval that's convenient for doing an integration. So it might be 0 to 2 pi or something like that. An abstraction is it's a Fourier series. I'm not really going to expound upon that, but just think about how you learned Fourier series way back in 2610, the very first signals and systems class. You learned that if you have a periodic signal, you can expand it out into a set of coefficients to represent that signal in a Fourier series. So in reality, we have like a Fourier series operation going on here. But that view is kind of abstract. I'm just saying, though, that when you learn something somewhere and then you see a very similar thing showing up, you say, oh, there seems to be a similarity, and sure enough there is. So just interesting in that regard. We have magnitude and phase of the spectrum, just like we have magnitude and phase of frequency response. It's periodic with period 2 pi. There's 2 different types of phases that we might choose to plot. The mathematical one is just the angle of the complex quantity. But generally what's going to happen is you're going to get this version of it. Arg is going to be the principal value, which means as phase ramps up or ramps down outside the window plus or minus pi, it wraps it in, because phase is always a modulo 2 pi quantity. there are times when we might want to use a function called onWrap, which is available in Python and of course in MATLAB. That will unwrap the phase, but I will explain that in a later chapter. We don't really need that right now. It's interesting to go ahead and try to prove that you can synthesize the sequence identically from its Fourier transform, and this seems like, why bother? Just believe it to be true. But this is just an exercise to prove that if I plug into the inverse Fourier transform expression, I'm initially saying x hat, saying I'm not confident I'm going to get back x, but let me put inside of the inverse Fourier transform that exact sum that we use to get the forward Fourier transform. So I put that in there, and then I can show that indeed the x hat of n does become x of n. The big question in here for a mathematician is, can I interchange the order of summation and integration? We can justify that if we go more deeply into real analysis from the mathematics side, but engineers, we do this a lot. Do you remember any time in your life where somebody said we're going to interchange the orders of operations, in particular in calculus or something? You might do one integral before the other one. You might interchange the order, like when you do 3D integrals. You might do, if it was in x, y, and z coordinates, you might do x first, or you might do y first, and so on. So here we're talking about interchanging the order of the sum and the integration. So if I bring the sum outside and bring the integral inside, which is what this is showing, so this is now going to be way here on the inside, and the integral is hunting down terms that involve omega. So the only terms that involve omega in this development here is e to the j omega n minus m when I bring those two guys together. And if I go ahead and just drill in on what that integral is, that's a sinc function. As it turns out, when you integrate the e to the j omega, you get the e to the j omegas back, and you have a difference in sign because you have a lower limit of minus pi and an upper limit of pi, and then you arrange that to look like a sine x over x function, and then that becomes the sinc function. But in particular, you look at that function and you say, what happens when n is equal to m? We're indeterminate, but again, using L'Hopital's rule, you'd find out that that's just going to be 1. And if n does not equal m, the numerator is always going to be the sine of some multiple of pi, which is always going to be 0, right? So it behaves, in this case, that behaves like delta of n minus m. And if that gets inserted back into here now, you get this, you end up proving that. You're just saying, oh, it just gets back the original sequence. Maybe that's not very amusing, but it's just giving you confidence that it's actually there. Why is interchanging order of integration and summation possible? It's a deeper mathematical term saying that we have uniform convergence when we're forming x of e to the j omega. And this, I'm not going to really elaborate on this. When I wrote these notes, I was much younger, and I had taken higher level math when I was getting my doctorate, so I got into real analysis, and I got into the details of epsilon and delta type proofs that some math professor maybe commented on during calculus somewhere in your life. There exists such that. You remember ever seeing that notation? There's a shorthand notation that mathematicians use, but I wrote it out here. But I said that for each epsilon greater than 0, there exists some n, namely the limit I would take it to, such that the difference between the approximation and the true function is less than epsilon. And if that holds for all values of omega, then that's a sufficient condition for convergence to be what I'm describing here as uniform convergence. The big thing that comes out of this, though, that I don't want to ignore at all is that absolute summability of the Fourier and the Fourier sum formula to get the Fourier transform ends up relying on this result. And where have you seen this result before? Where did we have it? Pardon me?
If the system is stable?
Exactly, except it was H instead of X. So this is going to tell us something useful that we'll be able to run with heavily from the frequency domain. It's going to ultimately, and this is not in this chapter, but it shows up in the next chapter, if the poles and zeros, or the poles of our system, and this is what we're studying in Z-transform domain, if they all lie inside the unit circle, let's say, then we'll be able to say that we know we're stable. If it's causal and the poles lie inside the unit circle, I'll get to that later. I'm just saying you might remember that from the S domain. Remember, the S domain talks about poles being in the left half plane for stability. Remember that? So, but it hinges back on this property right here, this absolute summability. So this guarantees existence of an absolutely summable Fourier transform. So this is the main point here. Stable LTI systems must have H of n absolutely summable. And we're also seeing that stable systems also have finite and continuous frequency responses. So that's how that works hand in hand. And then I'll extend that when the time comes later in the notes here. Unfortunately, things aren't perfect in the signals and systems world. That signals that we're interested in are not always absolutely summable, meaning under this blue box result here, and we end up admitting into our signals of interest other types of signals. Some signals are only square summable, and that is a condition that leads to mean square convergence, which says that in the limit, as the number of terms in the Fourier approximation or Fourier transform expression becomes large, the squared error goes to 0. But it's only mean square convergence. So in this case, what it means is that there might be points where it doesn't converge, but they're isolated points, and again, through finer points mathematics, that can be acceptable. And this you got a chance to get exposed to in Fourier series in 2610, where you looked at a square wave, and we're going to see there's a lot of similarity between that and what I'm going to look at in this next example, an ideal low-pass filter. Ideal low-pass filter cannot be built. We can approximate it, but for modeling purposes, we'd like to just say, let's just put an ideal low-pass filter in so we can just sketch out our block diagram for a system, and we know we'll replace it by a practical one. Can we work with ideal low-pass filters in modeling? The answer is yes, we can. We're just going to have to recognize that it's not going to be absolutely summable. And so I take the ideal low-pass filter, and I think I looked at a picture of this earlier, but Generally, we draw it on the interval minus pi to plus pi. So it's a filter that looks like that. I'm just drawing the sketch of what that expression tells us we have. The amplitude there is 1. So that looks well and fine. You'd say, I like that. I should be able to take an inverse Fourier transform of that. I'm using the definition of the inverse Fourier transform, and that's down below here. That is also well and fine. That's an easy integral to do, and it turns into the sinc function, just like we saw a little while back. So it says the impulse response is a sinc function that runs from minus to plus infinity, but it's not going to be absolutely summable. It's kind of like a problem that you see in calculus called the harmonic series. And the harmonic series is this form right here. Sum from 0 to infinity, say 1 over n, you get an infinite amount because of the rate at which it goes to 0 is not fast enough for a summation of the terms involved. Does that ring a bell? Because to me, I don't remember the specifics. I don't remember the professor. Calculus has good and bad memories in my mind, which for most of you it does, because I went to a quarter system school, so I had 4 quarters of calculus, whereas in a semester system you have 3. So you get to have 3 different people, right? Were they all equally good by you?
Can't remember, that was 8 years ago.
Okay, but I remember my first calculus teacher. I was just out of high school. I wasn't super strong in math, and I didn't pass the class. I ended up taking it over. It was taught by a graduate student who didn't really know what she was doing. She admitted that. It was tearful. She was in tears towards the end. It's like, I screwed this class up. What can I do? Well, what I did was just simply said, I'm going to take it over. And I had a really old, gray-haired gentleman for Calculus 1, and he was just excellent, and it made a huge, monstrous difference. I got A's all the way through calculus without a problem. It was just having the right person. But he was really good. Others were not necessarily as good, but I managed to navigate. I think it's also being a freshman, you're so naive, and I was a very quiet person, so I just sort of sank down because I didn't assert myself for sure, but you end up learning how to navigate college life after that, right? I mean, your first semester as a freshman is kind of a real struggle. And I have kids that navigated that, and yeah, pros and cons. I'm just remembering back, though, since I have twins. One was at K-State, the other in Kansas, the other was at Colorado State, and so mom and dad get to go visit both their kids, right, and go to all their events and kind of help them learn the ropes of things or cope with things. So yeah, somebody had a question, right, or no? Okay, so at any rate, it's a sinc function, and it's not absolutely summable. So what really is the ramification of that is right here. If we go back to that sinc function and we try to create the frequency response from the impulse response by forward Fourier transforming, we're going to have the sum of all the terms in the exponential, picture, I'm not going to write it down, I'm just going to go back up here. Picture the sinc function plugged into there, and we're going to try to sum that back up again. And I've already told you that it's not absolutely doesn't absolutely converge. So if you try to take the absolute value of that argument and sum it up, it's going to go to infinity. So there's no sense in trying to compute the Fourier transform of it as the sum runs from minus and plus infinity. But what you can do is just consider what happens along the way. So here I've just drawn some pictures to show you that If m is equal to 1, you get that, and dashed line is the ideal low pass. M is equal to 3, 7, and 19. I'm picking odd numbers because I'm wanting to pick a term that's above and below 0 plus the term at 0. So I'm just expanding it out. And the thing to notice here is that as the number of terms goes up, I didn't draw it super accurately, but the peak-to-peak ripple, whether it's just 3 terms or it's 19 terms, it doesn't change. It doesn't shrink down. Question?
Yes, sir. Is the magnitude the same? Is the peak magnitude the same in all those, or is
The mean, yes. Yeah, it is. Yeah. But it ripples at a different frequency rate because we've got higher frequency components in there. So this seems right now that this is a sad day in DSP that we can't build an ideal low-pass filter because we're seeing that we're going to have this rippling problem. We're going to end up, we can't take that infinite impulse response anyway and create it to run on hardware because we have an infinite number of terms. But to make it, first of all, it's non-causal, right? It starts at minus infinity, goes to infinity. Your first instinct would be, okay, I'm going to shift it to the right to make sure there are no non-zero terms to the left of n is equal to 0. You studied that in the first homework set, right? What makes it causal. Okay, so if I do that, I'm going to have to truncate it, so I'm going to have to make it be so many terms, like here I said 19. And then when I try to run that, put that on hardware and software simulation, I'm going to get this, all this ripple, and the ripple is also down here. So if we look at this in dB, the peak ripple, the largest one when it enters into the stop band, is only down 21 dB. Very poor rejection. You know, if you wanted to pass a signal and reject undesired signals, you're going to have this ripple that's going to just keep letting signals leak into your system. We can and will do better, and we'll talk about window functions later. I have a nice couple of examples of that in the Jupyter Notebook for Chapter 2 out of the book and the notes. And I'm going to look at that at some time. I'm not going to look at it instantly because I have another nicer application of this. But this is just something to know kind of in the back of your head. I can't do that. I do have an impulse response over here. It looks very buildable. I can solve the non-causal problem by shifting it to the right and truncating it, but I'm going to be very disappointed in the performance of it. So I have to do better, and there's methods to do better. Because there are certainly tools in Python and MATLAB and Julie that will design those filters for you, and they work well. They're not an ideal brick wall, but they can be made very, very close. So there's some neat mathematical things that can be done there. Okay, next example here is there's other types of signals or sequences that we're interested in that will result in impulses in the frequency domain. And these are of interest to us too because we already know that if you have a cosine in the continuous time domain, its Fourier transform is a delta function. It has 2 spikes, one at plus omega and one at minus omega. We have the exact same thing here. That requires another type of exception to the rule, allowing what's called a Fourier transform in the limit so that it becomes a spike, and I'll try to demonstrate that in Python too. So that's the nice result here. If we have a periodic impulse train, because we have to have a periodic spectrum, so this looks complicated. It's just saying that we're going to have spikes at plus and minus omega naught. then we have to consider that it's always going to be periodic. So if I'm just zooming in always to look at the first period, I just have to visualize with the dots there that it's just going to cookie cut place, up and down the frequency axis. And that's what the summation here is doing. It looks messy and everything, but it's just simply saying that we could have a whole collection like that out there. This is just doing a single, but I can do it for multiples too, multiple delta functions. And now I can take and get the sequence of this by inverse Fourier transforming, and I get back, this is the complex exponential, so I think I should have not included all of that in here. The complex exponential returns back to an e to the j omega naught. If I would have wanted to include an e to the minus j omega naught, then I could have built the cosine. So, and that I think, yeah, I have it right here. So here's the cosine case from Euler's identity that expands to positive and negative rotating complex sinusoids, and then that's what the spectrum would look like. So this is kind of the focus, the minus pi to plus pi interval, and there it is. Consistent with the continuous time case, except now we have the periodicities because of its discrete time signal. And you can make linear combinations of that too. So I'm holding up 3 fingers here to say the Fourier transform exists in 3 different ways. Number 1, and the best way, is uniform convergence, which relates to absolute summability and really a lot of nice set of properties. We use that almost all the time, but occasionally we want to introduce signals that maybe don't have absolute but have square summability, like if we want to model with the ideal low-pass filter. We have trade-offs, but it still can be done. And then frequently we want to work with periodic signals like cosines and sines and maybe other types of periodic sequences. They will end up having spectral lines in them which will be represented through delta functions.
The 3 are absolute summability, square summability, and periodic signals.
Periodic signals which we allow Fourier transform in the limit is what you'd want to write down. That's the third approach. How you get the Fourier transform, you have to get it through a limiting operation. When we go to the Z transform in the next chapter, though, we're going to basically not be very interested in looking at anything but uniform convergence, because that's the signals that work well. If we start messing around with delta functions and other things in the Z domain, things don't work well at all. It's kind of like just don't try to do it. It just doesn't work. But cosine waves are so popular as test signals, we want to have a way of handling it. And the ideal low-pass filter is popular for modeling. There's workarounds in the Z domain, though. It's messier to do that. So how do we deal with Fourier transforms when we're modeling in a simulation language like Python or MATLAB? We can do that, and we're going to use a function that's available in SciPy.signal, and it's the freq Z function, which MATLAB and Octave have. Julia has something equivalent to it. So we use freq Z. Freq Z is just getting the frequency response, kind of like taking the Fourier transform at discrete frequencies. So Python just modeled its name from MATLAB, because as far as I know, MATLAB was probably the first one to have this function in its library. So here I just created some simple test signals, 7-sample and a 4-sample. Wanted to say do the convolution of those two. I could do a direct analytical example of this where I would go to the frequency domain, multiply the frequency spectra. So we have the convolution theorem, which I'm going to describe here in a little bit, but I'm just simply writing it in here. So I plug into each of those and I get sinc functions for both of those two rectangles. This is sinc in frequency though, rectangle in time, rectangular pulse sequences. And I'm not going to try to inverse Fourier transform the product of the two sinc functions. That's actually fairly intense to do. If you're going to convolve two signals with rectangular pulse shapes, it's easier to just do it as a convolution sum. We know you get a trapezoid back, whereas I don't relish the idea that I had an inverse Fourier transform that. That's kind of a mess. I just pick this example to say, how would I get that frequency response? So here I use freq z, and freq z has the basic arguments that I will use will be A or B, B and A, and then I'm going to put in a frequency. So I'm going to put in a vector omega, and I will use that third one. And I generally don't use the other two. I generally don't use it to plot. So this is where if you read the strict nomenclature or help files for SciPy.signal and freq z in particular, sometimes you see notations that seem goofy, like this is totally backwards to me. It says the function returns an array of frequencies in radians per sample, and it returns the frequency response as little h. And your brain should say, no, that's not right at all. It should be capital H, right? If I'm transforming an input, I should get a capital letter for the Fourier in the Fourier domain. Just kind of ignore that. I think the authors of SciPy, which is 20 years ago, or around 2002 or somewhere in that time frame, they weren't all electrical engineers that did signal processing. They might have been physicists or mathematicians, and they didn't have the same love of the letters that we like to use. We always like to use capital letters for the transform domain and lowercase letters for the time domain. Am I right? I mean, that's what I was trained on. So when I first saw this, I thought, well, these guys don't know what they're talking about, but then you have to understand the context. The best way to see how this, and then this is the rest of the help. They give some examples in here. The best way is to follow some examples I created. So I like to not plot against omega. I like to plot against f because I'm sort of getting myself thinking into sampling theory. Okay, computer is stuttering at the moment, but omega is our radians per second, and actually, see, I've got it written right down here. So I like to plot versus f. So I kind of drive my freq z in a particular way where I create a range array f to run from 0 to 0.5, which is going to be equivalent to 0 to pi. I'll set the step size to be 1 over 1024, and then I will put in the numerator, or the b vector is filled in here, the denominator vector, the a vector is square brackets 1, but you can be lazy, and if you don't have anything but a 1 element array, you can just put in 1 and it lets you get away with that. Julia doesn't let you get away with that. MATLAB does. I mean, these are the things, if you switch around different modeling tools, you just have these little differences between the languages. And then what I do is I want to push into this omega, because that was the third argument. So I create my omega on the fly right inside the argument call. I write 2 times pi times f. And then you have to make sure when you're calling it, you're pulling out both variables and you're pulling them out in the order that it says to pull them out. And personally, I get confused because the order to me seems backwards. The frequency axis comes out first, and the complex frequency response, or Fourier transform, comes out second. You have to do that. And if you were to not put in both W and X, Python will return to you a tuple variable which contains 2 variables, and you'll have to parse it apart yourself. I'd recommend not doing that because that's confusing. You'll get something and all the information will be there, but then you'll have to unpack it. So by doing it like this, W and H, you can unpack it. And what I do, again, it's just me, I go through and I say, it's going to give me W. I don't really want it, but I'm just going to ignore it. It's always going to give me in radians per sample, and I want to use F instead. So I've already created the F to start with. It's going to return that W. I'm just going to ignore it. I won't use it for anything, but I will use the X. So then I can go ahead and plot the absolute value, the angle, the real part, the imaginary part, and so on and so forth. So something like this. Here's for the rectangle. It's giving me the alias sync that we talked about briefly at the end of the class last week. For the magnitude, it's giving me the phase, which is a linear phase, and then real and imaginary parts happen to look like that. And this one here is just H. That was the second calculation I did in here. This is the calculation for H, and the first one was the calculation for X. And then I went ahead at the very, very end of this. I said, let's just multiply them together so I can get Y. So Y here was obtained. I think there's the last line of code in here where I just multiplied it together to the magnitude response of X times H. And Python is very generous here. If you want to take 2 arrays that contain complex numbers, you can just multiply them together, and it automatically does them point-wise. MATLAB would require a dot in there somewhere, and Julia requires a dot in there somewhere, but Python is pretty generous on that. Now, if X and H are of different lengths, then you're going to get an error from Python. It's going to say they're not compatible, and you've got to fix that problem. At any rate, this comes out very, very quickly, and it's used a lot. So maybe I should take the break earlier today. I mean, this is a breaking point where I'm going to go talk about theorems, and I might come back and look at some examples. So this is running, and I'm going to use my handy index over here. Now I'm in the wrong notebook. It's my index over in this notebook. This Chapter 2 notebook, which is up there on the website, it's got the time domain modeling stuff in the very top of it, and then frequency response stuff starts down below. So when you're looking at a bigger notebook, rather than scrolling for something, you can always click this little box, switch from the file view to the table of contents listing, which you can do different things in here. You can collapse headings. I mean, there's a lot of different options, but you can put numbering on if you want to, too. Notice that. It's like you're writing a book, right? You can do fancy things like that with Jupyter. But at any rate, I wanted to go here, and we'll talk about this example when we're looking at some theorems. But I think now would be just a good time to take the break, since we're timing up pretty closely to right in the middle, and I can answer questions or discuss anything else that's going on. And you can also let me know if you want to which homework problems you're already wanting to ask about later, so I'll know how many and which ones I should be heading towards. So I'm going to stop the video and we'll start it up again after the break. Okay, we're back. Started a new video by accident, but I'll fuse them together. So we were just going to look at a couple of things in the Jupyter to get started with using FreakZ. So I can go off of this in the notes, or I can go off of it right here. I'll just go off of it right here, and so I'm going to do it right here. If this is big enough, is it big enough? I have this same math in the notes, obviously, but I moved it all into here. I literally cut and pasted it into here because my notes are written in LaTeX, and the mathematics that you do in here, this is all LaTeX syntax. It's a markup language of sorts. So so it's pretty easy for me to do that. At any rate, an example that was taken in here is first-order difference equation. Using either recursion or classical solution techniques, we know that the impulse response for this first-order difference equation, y is equal to a times y of n minus 1 plus x of n, absolute value of a less than 1 for stability, is going to be this a to the n u of n. And if you don't like getting at it from that way, you have in the homework problems that are due on Friday, we could Fourier transform both sides of the difference equation and eventually convert it to the ratio of y of e to the j omega over x of e to the j omega, which is the same as h of e to the j omega. We'll get back into that shortly. So that's another way of getting at h of e to the j omega, and then you would inverse Fourier transform that to get a to the n u of n. But right now we're going in the forward direction. We're saying we don't have h of e to the j omega. So I'm rambling a lot, but in the homework problems, you're given maybe a difference equation in one problem, and it says it wants you to get this. You could go over to here and get h of e to the j omega by Fourier transforming and forming the ratio of y over x. And we'll look at that in another example. But at any rate, I have it here. So suppose I had to do the forward transform. I plug that into the definition. I put the a to the n inside the sum. That's the definition of the forward transform. And then the u of n up here just says, okay, the limits are going to be controlled by that u of n, go from 0 to infinity. And then I wrap a parenthesis around the a to the n, e to the minus j omega, and then put the n outside of that. That's just simply rearranging the math. And now I recognize from this that this is a infinite geometric series, and this is the ratio that we've seen before. This is R. R is now a complex quantity, but the geometric series still converges under the condition that magnitude of R is less than 1, And we know that's the case because we said A has to have magnitude less than 1. What's the magnitude of e to the j omega? It's 1, right? It's a complex value that has magnitude 1. So this is how it sums. I have more detail on, I guess, the geometric series in the notes, but remember I said that the geometric series will keep coming back again and again. So this is this first order difference equation, a to the n u of n becomes in the frequency domain 1 over 1 minus a e to the j omega. And I think I'm missing a minus sign in there. Yeah, I'm missing a minus sign. So I can fix that. Did I fix it? Now I'm getting myself confused. Yeah, now the minus sign is in there. It has to be there. I mean, it didn't look right to me. I just made a typo. At any rate, we can do a number of different things before we go off and plot this. We can mathematically write it all out in terms of magnitude and phase. We can get the DC response. This is part of a homework problem. So to get the DC response, we just set omega equal to 0, and that will be h at 1, because that's e to the j0, and I replace e to the minus j omega now with just 1, and I have 1 over 1 minus a. So this system has a DC gain of 1 over 1 minus a. What I like to do for plotting purposes, I like to plot things with unity gain, so sometimes I will normalize the gain. So I can just simply write the normalized gain by scaling by 1 minus a out in front. So how do I plot the frequency response? I just set up, like I was showing you before the break, right here in Jupyter. I'm going to do a range from 0 to 1/2. I'm going to double the resolution on this to 2048, and a equaling 0.8, and now I'm going to plug into freq z. So here I'm just going to put the DC gain that I have right up in here, 1 minus a, just let that be my b vector. So I could also have written b is equal to 1 minus a if I wanted to, and then I could just put b in there if you like that better. The a vector is actually composed of two components. It's always going to have, from our difference equation, if we go and rearrange this difference equation, we would move this term to the left-hand side, so we would have 1 times y of n and minus a times y of n minus 1. So that's all I've done here, to remember the standard difference equation form. So that would be the official a vector, and the little a here is just a parameter that's in our coefficient vector. And then I'm going to evaluate at normalized frequency f, and I'm going to do 2 plots, a subplot vertically stacked to be magnitude on top, and then phase on the bottom, and I'm converting phase in radians to phase in degrees. So if I run this, it should come back at you instantly. Computer is just acting amazingly slow, but there it is, magnitude and phase for our first order low-pass filter. What's special about this first order filter is it is a low-pass filter, but all I have to do is change the sign of A, and it will become a high-pass filter. So suppose I make that a minus, it's going to, the math form doesn't change, but you'll see now it's just the complementary filter. Does that make sense? To get a better appreciation for linear systems and sort of thinking back to hardware, here I'm going to take the same example. I just have, instead of doing a freq z on it, I'm going to use L filter, and I'm going to create a sinusoid that's at this normalized digital frequency of little f naught being 0.02, and I'm going to generate that over 200 samples. I'm going to just pass it through my filter using L-filter, and then I'm going to plot an overlay plot of the input X and then the output Y. Why am I doing this overlaid like this, and why I'm connecting the points now, something I said you shouldn't ever do, but I'm saying it's okay when you're trying to draw a particular interpretation. So by connecting the dots, what I'm trying to emphasize here is, first off, the amplitude of the input is plus and minus 1 peak. The output is a little bit attenuated, and for a low-pass filter, we're operating at 0.02. So let's go back over here to get this set up right to be the low-pass filter again. Something you can observe from this. Okay, we're at 0.2. So I have this in dB. Maybe I don't want it in dB at this moment, so maybe I'll just take that off of there. Let's just play the game this way, put that in. Remember, this is my way of hacking my code. I don't delete anything. I'm going to comment a line out, and now I'm going to take off the dB conversion here, and wait for it to come out. So we're at 0.2 normalized digital frequency. Our gain is about 0.2. You following what I'm doing? I'm just seeing, if I put in a sinusoid, I messed that up, 0.02, right? So maybe what I should do here is to get a marker on that, I could put a line in here, but I still can't read this cursor. There is some things they've added so you can have cursors move around on here, but let's just do something else that I think might be helpful to you. I can go down here. Suppose I'd like to figure out what is the gain. I think I've actually already done that. Never mind, I've already done it. See, I thought my brain works the same way every time. I wrote my notes and I'm doing the same thing. So what I'm interested in doing though is figuring out what is the gain at a normalized frequency of 0.02 and what is the phase. So here I'm wanting to see, is this orange peak on the output about what I expect. And I'm also going to look at the zero crossings of the input and the output compared. So I'm seeing that the input is here and the output is phase lagged slightly because of the phase shift applied by the system. So I go down here and I use freq Z again to just evaluate at two frequencies, 0 and f naught that I used up above. And then I just have it print out the absolute value and the angle, and it prints out two lines, and I just interpret it as, okay, at DC, my gain is unity because I normalized it with a 1 minus A, and at 0.02, my gain is 0.64, and my phase is 0 at DC and minus 46 degrees. So this value right in here is nominally, the peak value is about 0.64. And what's this going on here? What do we call that? From systems theory in general, starts with T. System is going through transient, right? It's charging up and getting into steady state. So the first cycle is jilted slightly because the system was at rest and wasn't charged up at all, but then it gets into steady state. And that's what the Fourier transform is all about. It's a steady state frequency response. So, and then we could draw vertical lines on here if we wanted to see how much of a cycle, say the zero crossings are varying by right in here. And in theory then, if we take that length in fractions of samples now, which is kind of kooky, but you can do it if I was to draw vertical lines here, and then compare that to the length of one full period, like this zero crossing to the next negative zero crossing, that ratio of this length to the full length is 1 period, which is 2 pi, and then I could get that to be how many degrees of phase shift. And it's a negative value because it's lagging, and that should be this minus 46 degrees. Does that make sense? So anything you've learned before still applies in the discrete time domain. I mean, you can get those warm, fuzzy feelings. And there is one homework problem where you have to do some of this type of analysis. So now I'm going to jump to the next example, but I'm going to go back to the notes for that because that has some more math in it that I want to do over here. So in order to do more transforms and to do more things more efficiently, we have to develop some Fourier transform properties, and the first thing that shows up in the notes is symmetry properties, and then on to some theorems. So one of the properties for sequences has to do with symmetries, and there's a large collection of symmetry properties that are described in the book and less so in the notes, and it has to do with whether or not a sequence is conjugate symmetric, which is this definition, or conjugate antisymmetric, and it just says any sequence is composed of conjugate symmetric and conjugate antisymmetric, and then you can go on and kind of live your life thinking in that level of complexity. I prefer to just think of the real case because that's the most often case that you deal with here. And this is what you already are familiar with. If x of n is real, then we just say it's an even sequence if this is true. In other words, it flips about the axes and it just is an even function. And if it changes sign when we flip, we call it an odd sequence. So I prefer to just stay with that basic property for the real sequence case. So again, under the transform decompositions, if you go to the frequency domain and just focus on the real case, I'm not saying you won't ever have a homework problem where you have to deal with the more exotic forms, but most all of the time this is what you're doing, and this should just become second nature for the real signals case. So the important result for the real signals case is that the magnitude or the frequency response is conjugate symmetric. So as you go from positive to negative frequency, all that happens is that the phase flips in sign because it becomes the conjugate of the value at the positive frequency. Magnitude response is even, and the phase response is odd. And then furthermore, the other real symmetry cases are if x of n is even, then its Fourier transform is strictly real, its imaginary part is 0, and if it's odd, its Fourier transform has got a real part 0, and only the imaginary part exists. These are things that you learned at the beginning in 2610 and elsewhere. I mean, I'm assuming that you still hold those in your brain somewhere, maybe weakly, but they're still there. They're way back there. You'll see them in action, though. So this is a full-blown list that appears in the book that is all the different types of symmetry properties. We've just been focusing on the real signal case, which is, to me, the most important one. So this example we already did in the Jupyter Notebook. This just goes in a little bit more detail of how I went about getting things. This goes into a little bit more detail about how I got the magnitude and phase, and you can get the real and imaginary parts, just standard algebra things where you multiply numerator and denominator by, say, the conjugate, and that way you can make the denominator be real. That's what I did here. And then you can break it into real imaginary parts. There's lots of different decompositions. You have to use things from your past to just manipulate complex values around. But this demonstrates for this simple a to the n u of n response that it is indeed even in the real part, odd in the imaginary part. The magnitude is even in frequency and the phase is odd in frequency. And as A gets closer to 1, then it becomes a more narrower low-pass filter. It's an approximation. And actually this difference equation in this impulse response is related to the analog RC low-pass filter. So you can draw an equivalent there between R and C and the sampling frequency, and I'll save that for later, but this would be a simple synthesis of how you would come up with a digital filter that approximates an RC low-pass filter. There's just an equivalence there. And it basically boils down to, I'll just write it out, but I'm not going to. This thing's really sluggish right now. Comparing those two, where A would be a time constant in the right-hand side, and A is just the coefficient in the left-hand side. So those two A's are not equal to each other, but you can make that equivalence if you wanted to. Actually, I guess the way it would be, now that I'm going to get going on it, I'm drawing that it's taking an eternity to give me a response. Remember that for an RC low-pass filter, you have e to the minus t over RC for its impulse response. So then you can equate these two together. Why has this gotten so bad on me? I don't know. Almost can't use it. I can't use it right now. Maybe there's a problem with the pen. It's not going to work for me for now. But let's just see if I can do this. Draw it. Fs being the sampling rate. So now I have enough information to go back to that red equation there and be able to relate A to RC and the sampling frequency, because I can just make some substitutions in there. I can replace T by NT, or N over Fs over here, and then I can factor it in such a way that I pull out the exponent as just N on both sides, and then I will have A related to, like I said, RC and sampling frequency. Does that sound reasonable? It's kind of a cool thing to say, I know how to build an RC low-pass filter in the discrete time domain. I mean, it's just drawing that relationship right here. So transform theorems are the more powerful tools, and I didn't limit you on assignment number 1, but a number of you have went ahead and took your liberties. I wanted you to solve by recursion, let's say, and you decided to go through the transforms. By me, that was jumping the gun, but I didn't say that I didn't tell you not to do it. The recursion was my intention, though. At any rate, the theorems would be at the script F is what we have here, and if you're ever into this in Jupyter, let's say, let me just do something silly for a second here. Make this a markdown cell. So So if I want to do math in here, I would delimit with the dollar signs, and then I can go Math Cal is the tag that says I want a calligraphy mathematics symbol, and there it is. So there's a lot of stuff on this, different things you can do. And if I wanted to write it as an inverse, I could go, and then if you have two characters you want it to be in the exponent, you have to delimit that with a curly brace, so I could put a -1 in there. And now I have inverse Fourier transform if I wanted to write that out. I'm not saying you have to, I'm just saying that there's a will, there's a way, and there's a lot of power, and you can use math in your notation over here. You can see how in this particular figure that I rendered, well, I guess I haven't rendered it yet, but when I rendered this figure, you can see how right inside the label, and that's the reason for this R, when you put in the label, that tells Matplotlib, the graphics library, that I'm going to give it a string and I want it to be interpreted as a raw string. So R means raw, and it's because I want to be able to put in strings that contain some LaTeX mathematics. So, and I'm going to delimit those LaTeX strings inside of this string with a $sign again. So here I have E raised to the curly brace J, and then /omega is going to be the lowercase omega, and that will render out to be that. Is that cool? To me it's cool because I can be very specific. I can create nice figures. In my meeting yesterday I did all that stuff so that the figures looked nice as I was changing things on the fly, and we were trying to discover what's going on. You can also take this further and you can interpolate a value into here if you want to. So let me just do this once, since you'll never have to do this again if I show it to you right now. Let me just decide that I'm going to put that in on its own. So I'm going to put in a little string of mathematics that has the italic, and then I'm going to put in a character string. And there's different ways of putting in numbers into strings, and oops, I'm going to use the old school one because to me it's more like doing it in the C language. So I'm just going to do that, and then I'm going to go over here and I'm going to have a tuple and I'm going to say that's the symbol, and if I only want to have one I can put it by itself, but this is a trick on tuples. If you just put a comma and don't put anything next to it, it treats it as a single element, but if I want to put in more, I could do that. So what I would have done up here is I would have said m is equal to 5, and then I would have just spread my m into here. All well and fine, but now what's going to happen when I run this, it's going to fill m equals with that's the C language and other languages too, delimiter for a decimal value, a digit, whereas I could use F as the formatting string for floats and things. So, and so that 5 right now is going to change handily if I make this 10. Is that, I don't know if you like that or not, but it's handy to make your notation change, and maybe I don't need this space in here. Yeah, that's a better spacing right there. I don't need the extra space because this string has an extra space at the end of it from the LaTeX math, so that looks nicer. Again, if you're a graduate student, you publish papers and you want to produce figures, maybe in Python, and this makes you be able to get graphics that are really nice. As a matter of fact, another little story is if you want to get this plot right out of here, you can go save, hit tab, and I believe it's say fig. Just make sure I've got that right. Yep. So let's just give that a name. Let it be a PDF fig, and this little line right here to matplotlib will tell it I'm going to create a PDF figure because I've already given it a string and it has the extension of PDF, so it picks up the fact that it's going to be a PDF. If I said PNG, it would do PNG, and then I could add an optional argument that would say how many bits, what resolution do I want. So when this runs, I've got this turned back on again, so I'd have to be wherever this notebook is at, which I don't remember where it's at. We'll figure that out here in a second. Where in the world am I? So put in another cell here, and I can type Unix-like commands. PWD gives me my path. It tells me where I'm at. I'm in this Julia Python folder, which I'm already into it, so I guess I'm good. So my figure was named my fig, and there it is. Created 24 seconds ago. I can double click on it, and there's a previewer built right into Jupyter, and there it is. So that figure is now, I can take it somewhere. So everything you didn't want to know that you can do, professors have to figure this stuff out so we can produce documents for students and write papers, and it goes on and on and on. But it's part of the package deal. You got to have enough stuff to really be viable. So going back over to this, these are the standard notations. X equals script F, little x equals script F raised to the -1, signifying inverse transform. And then a pair would be x corresponds to x of either the j omega with the script F on top of the two-sided arrow, which in LaTeX is something like left, right, slash, a backslash, left, right arrow, and then you can do a long left, right arrow. So this is a longer one, so it's got more width to it, and then you can wrap that up inside of a, let's see, what's it called? Stack or something like that, where you can stack symbols on top of each other. Why is LaTeX so pervasive? It's been around for a long time, but now it's found its way into Markdown, and it's found its way then into Markdown so that you can put math right in web pages. So the language itself was developed a long time ago. I learned it a long time ago, but it's surviving because it's now available within Markdown, and that's how you're able to use it here. So it survives. There's been other languages that came along, MathML, which hasn't really taken off, or didn't take off because somebody got on the bandwagon with this stuff that seems to be more popular. And I like it because I learned this a very long time ago, and I just keep using it, so you just keep you have memory of certain things, and then I cheat and look on the internet for symbols and things in LaTeX. So first transform pair is linearity. It just says Fourier transform of a combination of signals is that same linear combination of the individual Fourier transforms. Some theorems that are really popular. This one here, the delay theorem, is very popular, very essential in the homework. So when you Fourier transform with a shift of the time axis that pulls out this term out in front, it's just a linear phase term if you shift. Same thing in the continuous time domain. Frequency shift, very popular. It was in my presentation yesterday. I'm going to take a signal x of n, and I'm going to bring it through a multiplier, which represents that. So it might be something I'm feeling like my computer is grinding to a stop with the video, and I think that I didn't put it on the low resolution, but I thought it was. So I think that's what's happening. It's just about ready to crash.
Well, the projector hasn't crashed today yet.
Yeah. And they didn't write back to me on the ticket. They were supposed to write back to me when the ticket was resolved, and they haven't told me it's resolved. So my understanding is it's not resolved yet.
I mean, is it too early?
Yeah,
I don't know.
There's still time.
There's still time, yeah. I have a feeling I'm running at the high resolution. I apologize for that. It's going to take longer to produce the video, too. At any rate, so that would just be a symbol of that. X would go in over here, and that would be a translator which in an FPGA could be generated by some numerically controlled oscillator that would then be driving a sine and cosine lookup table so that it would produce a complex sinusoid. Inverse Fourier transform, that is a way of getting at the proof of that. Parseval's theorem, just stating that. We're not using it right now, but it just says the energy is equivalent between the time and frequency domain, and it relates to the energy density spectrum, is what this quantity is right here. When we discuss random signals in Chapter 4, we'll be looking at the power spectral density too. And that's just a proof of that. This is a very big one. Use this a lot. Use this a lot in the homework. It just says that the convolution between two signals can be in the frequency domain is the product of their transforms. And we can take this backwards, and we can rearrange it so that if we have a system like this, we can rearrange it to say that h of e to the j omega then is, just from the algebra, just reworking these things, y over x equals h. And you're going to use that multiple times in this homework. And then you're going to inverse transform that back to get a sequence domain, and that will be using the time shift theorem. So that's very valuable.
I have a question, Doctor.
Okay.
Because I ran into this while doing math, if we come up with a crazy expression that we were not able to inverse Fourier transfer, do we just leave it there, or?
Yeah, but what I'd like you to be able to do, though, is use geometric series properties and just use basic algebra to combine things. So, and I want you to do that. I assume we're going to get some time for the homework, and I'll maybe just illustrate how getting it into a form, a nicer form, is something I want you to try to do. Just don't leave it in sort of a chunky-looking form when you can simplify it. There's logical things you can do by factoring something out and then forming a cosine, let's say, and things of that sort. Okay, this theorem, modulational window theorem, is useful in understanding how to solve a couple of problems. One of the problems is we were having with the ideal low-pass filter, we can do something called windowing. So we can take advantage of that, and that would be windowing in the time domain. So that would be like the dual of this. This example, modulation or window theorem, relates to the idea of how you can understand the impact of the window in the frequency domain and how you can get better spectral resolution. So the importance here is that we will have a window present in our filter design. So we're not just going to take x, like that sinc function, we're going to multiply it by a shaping function, a window function that's going to try to drive it down, taper it down so that we can reduce the side lobes, and that will help solve the problem of that ideal low-pass filter. And then the impact of that shows up over here in the frequency domain through this windowing theorem.
Is that the theory behind the spectrum analyzer window?
Yeah, yep. It should be the same. You're talking about on the scopes? Yeah, you see Hamming, Han. Yeah, that's exactly that theorem and how that is practical. The rectangle is sometimes called the boxcar, but in this example here, that W is the window, and it could just be a rectangle. So it just takes like the sinc function that's doing this, and you just chop it, which is very abrupt. If you taper it down with a raised cosine or a triangle or many, many other shapes out there, then you can make the side lobes less. And you're making me think of something that I wanted to make sure that you saw in the Jupyter notebook today too. So turn that off. I do have a good discussion of windows in here, and I think, yeah. If you want to see all the windows you can choose from now, you can just go into right here. I just put signal dot windows because now they're in a separate folder effectively in the library for signal, but the dot is just listing off. These are all the windows that are built in to SciPy.signal. And Boxcar, for example, shift tab on that is just a rectangular window. You have to be thinking of trains, a boxcar and a train, but Han, let's see, it might be Han, NN. Yeah, that's what it is. It used to be called Hanning, and here they teach you a lesson on spelling and translation. It was Hanning's window, so it became known as the Hanning window, when actually the guy's name is Hann. So in some languages, scientific programming languages, they have both Han and Hanning, and I learned it. It explains it, though. They wrote that into the help. That happens, right? Because we're English speakers, and we tend to just develop slang of some sort or another. In my old age, I'm amused by things like that, especially when it comes to acronyms, how there's so many acronyms that get reused, and how it makes it funny when you know it one way and somebody else says, no, it means that, and I don't know anything about that necessarily. I just know it is an engineering acronym. So the theorems are summarized here. There's not that many, and this is what's on your cheat sheet, but we will use the delay theorem. Linearity, of course, is used all the time, and the convolution theorem is very popular, and then the window theorem occasionally. Then transform pairs. We haven't really developed very many of them, but we've already seen this one. We've seen the delay theorem, so this is just the delay theorem for a delta sequence. Yeah. I haven't proven that one, and that one I think comes up here in a moment. I talked about it last week. Cosine is down here. Complex sinusoid is up here. So these look messy in this terminology because they're trying to show up for all values. If you just look at the fundamental frequency interval, you just get one delta out of here, and you get two deltas out of here for the cosine, one at the positive, one at the negative. So how can we use the delay theorem, a to the n u of n minus 5? This is kind of like a trivial example, but it just shows you how you should be thinking in terms of the theorem. So what you can do is let this be a to the n minus 5, and then pull out an a to the 5, and that would be works through linearity. But then you can just focus on this and say it's going to be the Fourier transform of a to the n u of n, which is this guy, and then the time delay theorem says you have to add that on, and then this was added on just as a means to do that refactoring. Sometimes it's silly to do unnecessary things, but this shows you how you can work things like that. And then if you want to get the Fourier transform of that, all of this stuff here just from linearity sits out in front. So you just have the Fourier transform, the a to the n u of n, which is 1 over 1 minus a e to the minus j omega, and then these are just your scale factors that sit on top of it. I'm not trusting my clock. I can walk through this one. This one, I guess I've got plenty. I think I have a fair amount of time, but I can go burn it up really fast here. Some of these examples I definitely want to drill onto, but I don't want to shortchange the opportunity to talk about any homework problems. So I'm feeling like I want to jump off to make sure I don't shortchange that, even though only half the class is here right now. I'll let you be the representatives. Do you have any questions you want to bring up to me on the homework? I mean, I gave you the hints page, and I have my tablet here. I've got the solution sitting in front of me right now. So I can elaborate on some things if you want me to. Even though I'm handicapped because I think I'm processing too many samples per second for my frame capture. I'll just jump back to the notes though for a second. Something that is an example that shows up after this example. This is a little bit more exotic example, but I like it because it talks about filters and realizing filters. This 222 is very useful, and it's a technique that you get to use in maybe 3 or 4 of the problems. You can start from different directions, but suppose you're given a difference equation and you want the frequency response, you just simply Fourier transform both sides of the difference equation using the delay theorem. So Fourier transform in a symbolic way is just y of e to the j omega. Just assume that it exists. Here's our episode of silence.
Yep.
The projector has died, and I'm waiting to see. Yep, okay. Have to give it a timeout, and it's turning back on again. If you're watching the video, you didn't notice anything, except you heard me talk about it. At any rate, you just symbolically operate. So we symbolically transform both sides of the difference equation. We have this, and if we want to get h of e to the j omega now, all we have to do is form the ratio of y over x through algebra, and that's what I've done down here. If you want to get the impulse response, you would inverse Fourier transform h of e to the j omega, and I would then use linearity to break it into 2 terms, a 1 in the numerator and a 1/4 e to the minus j omega, and then you can inverse transform using a to the n u of n for those 1 over 1 minus 1/2 e to the j omega terms. And then you've got an additional factor on the second term because that there's a 1/4 scale factor, and then the e to the minus j omega means a 1 sample shift. So, to see how that works. And if you need to go back the other direction, suppose, and this is true in homework problems, suppose you you start here, you start with your given h of e to the j omega, now you cross multiply y of e to the j omega times that denominator and x times the numerator, and then you're just working backwards through this. You're going to have this guy, and then you inverse transform term by term, and now you've got the difference equation, if you need to get the difference equation. So lots of different ways to mix and match with this, and this is certainly what you do in problem 1. You get to do it in problem 2 because I give you the option of not doing the classical solution, but instead you could get it through impulse response, where you have to get h of e to the j omega and then inverse transform it into the impulse response, like a partial fractions thing. So that works well there. In the second problem, that's 2-9. You also have to get the step response. You can get that with the classical solution technique. If you have time, I'd definitely explore it because you can just sort of expand your horizons. The alternate approach on that one that I suggested is just accumulating the impulse response to get the step response, and that's going to mean doing 2 geometric series. Right? I talked about that last week. Just suppose it was like this. What I said you have to do is you have to use K in here. You should be starting at minus infinity, so I already took care of that. You're going to accumulate from minus infinity up to n, but that u of n makes you start at k is equal to 0. So now you sum that up, and that's the finite geometric series, right? Is that right? The finite geometric series. Add 1 to the exponent in the numerator, because there's a total of n plus 1 terms in this sum, and then the denominator is just 1 minus the ratio. So you'll have 2 terms like that in the homework problem, the second one. Third problem, some of these same exact ideas. One of the things that shows up in this third problem, though, this is 236. It asks you to do 2 things in particular. It says you're given an input that's composed of a DC term Definitely, I screwed up today. So hard to get it right. Got to shift it back. I wanted to use this tablet at the higher resolution mode, and I shifted it back, and I thought it was automatically shifting when I plugged it in, but it wasn't. At any rate, in 236C, this is now switching back to the time domain, but we're thinking of steady state. So when we apply this to a system, when we want to think about what that's going to come out at over here, y of n in steady state is going to be 4 times plus 2 times, and I'm going to have to put in cosine, and then I'm going to have I'm going to have to mess around with this, so I'm going to have to go sorry, I'm double writing because it's not responding quick enough for me. I'm not quite writing that out right, but another term has to be in here. You have to break the cosine into the real and imaginary parts, but actually you just want the angle in there, so I didn't do that right. Fundamentally, though, what you need to work this problem is it'll cooperate. For this problem, you want to figure out what value of omega naught, you want to figure out what value of omega naught you need to make that equal to 0. And you just look at the analytical expression for the frequency response, and you can see how you're going to drive it to 0 for the frequency response. There's a bonus problem in here. Pretty cool bonus problem, actually. I made it a bonus problem because it's one of the advanced problems. But the last problem, 258, is using transform ideas just like we already talked about and looking at stability and so on. That's problem 258. The second to the last bonus problem, though, is what's cool about it is that if you try to work it in the time domain, it's almost impossible to do. If you work it in the frequency domain, it's very easy to do. So what you end up doing in that problem is they want you to find out what the impulse response is for this system. No, that's not what the question is. It's not impulse response, it's just y of n. So to work this problem, this is going to be h of n, right? When the delta fires through here, you get back h of n because that's a filter that has that frequency response. So then time domain, you'll have h of n. The spectrum at this point is going to be h of e to the j omega. And then what you're doing is you're passing this signal through this operation and then no operation and bringing them together through addition. The special hint here is that, and I put this in the hints page, e to the minus j pi n is exactly minus 1 to the n, because e to the minus j pi is going to be minus 1, or e to the plus j pi is exactly minus 1. So if you visualize that minus 1 to the n as being a complex sinusoid, now you're actually frequency translating the signal that flows through that upper branch. So you're shifting it in frequency by plus or minus pi, and the lower branch is not getting shifted. And so what you want to do is you want to draw out in the frequency domain what does the spectrum look like on the upper branch and on the lower branch, knowing that it's an ideal low-pass filter that's in the model for h of e to the j omega. And you're going to see something very interesting when you do that. From that picture, then you'll be able to say, I know exactly what's happening. And then you'll be able to write the answer out. You can actually write it out directly in either case, but you want to think about what's going on in the frequency domain. I'm not being I'm being fuzzy on purpose because it's a bonus problem, so I can't lay it all out. I want you to just think about it. It actually works out really well, and it's kind of a trick problem in a way. Okay, still have a few more minutes. The last problem, like I said, is just more of the same. It's an FIR filter that has 3 coefficients, so that's 258. One part of this problem, though, that I want to make sure that you are aware of is part B. It asks you, is this system stable? So, oh, I'm thinking of a different problem. Never mind. This one is obvious. This doesn't have an issue with it. I'm thinking of an earlier problem. I'm just thinking back to grading and how this gets overlooked. It's this other problem. Problem 254. In problem 254, which is problem 3, it asks you to find out, is it causal, or prove that it's causal. You'll be able to find out if it's causal using the same theorem that you used for LTI systems in set number 1. To prove that it's stable, you have to look at the impulse response and consider a couple of constants that are present in the impulse response, and you have to tie down both of them. So just be rigorous on this. I mean, if you have a signal going through a gain, capital K, let's say, and you wanted the output to be stable, to make that stable, you just have to make sure that gain K has an absolute value less than infinity. But don't ignore that fact. It's just a fine point, but, you know, just tie it all down to make sure what are the conditions to make it stable. I think that covers that stuff. Before we leave, I guess we didn't quite get to the Z domain, but I do want to point out a couple other things that are in this chapter. Discrete time Fourier transform of a periodic impulse train is something that you can find the Fourier transform of. So if you wanted to find the spectrum of a periodic impulse train, or in a sequence of delta functions separated by m, then you can find the spectrum of that, and the spectrum of that is going to be motivated by finding an impulse train in the time domain. But if you do it in the frequency domain, or the discrete time domain, I mean, you're doing this, and what you end up showing is that if the impulses occur at every one sample, then every m samples, I mean, then the spectral lines will occur at multiples of 2 pi over m, or if you normalize it, 1 over m. The windowing I want to spend more time on, but we've got 5 minutes, so let me just go off and diverge on something for a second in Jupyter. I may have this down, but it seems like I didn't do this. I do have more examples at the bottom, so I'm just going to go do a little example here to show that interesting property. So I'll create I'll start off by creating just 10, and then I will I'm going to be cheating a little bit. I'm going to be using a function that we'll see in Chapter 4, but it's just a simple way of getting zero stuffed in between. So I'm going to take x1 actually, let's not worry about creating an axis right here, right now. Oh. Oh, I forgot to say I was going to upsample by 10. What am I doing wrong? I did something obviously wrong. Oh, I know what I did wrong. I needed to say that needed to be the length of that. Okay, so there's a bunch of 1s, but now if I just make that be x2, you're going to see what happens as a result of upsampling. I'm putting 9 zeros in between every one of the 1s that went in, so I'm upsampling by a factor of 10, and this is kind of like the periodic example that I was thinking of here. Now if I go ahead and wanted to show that the spectrum of this would be of an impulse train in the frequency, I could Fourier transform this and we'd see that in the frequency domain. So I'd have to, I don't know, I'm going to punt on this. I'm going to be over time and I can hear the noise out in the hallway. I'll maybe add this in the notebook before I repost it again. I was going to try to just demonstrate that you can approximate this spectrum where I'd be able to see all these spectral lines in there. And I was also going to show you how you can use freq z to approximate the Fourier transform of a sequence by just loading the values in to the B vector. I do show that in the notes, though. That's showed in another location in the notes, and I think it's in the notebook examples. I'm out of time, though. I'm going to declare I'm out of time.